Okay, I hope everybody's enjoying their Thursday off on Veterans Day. And let's have a look at the homework from this past week. First problem is about predicting whether the entropy of this chemical reaction has seen an increase or a decrease. Has chaos increased as we measure with the entropy, the disorder, or have things become more ordered and the entropy therefore decreased? Well, one of the ways we can look at this reaction is to think about the number of moles. There's 1 mole of the C2H2, there's 4 moles of the fluorine, so going into this reaction is 5 moles. Being produced, the carbon tetrafluoride, we have 2 moles plus a 1 mole of hydrogen gas, so there's only 3 moles of matter being produced. So the number of moles in the reaction has decreased. Matter has become more ordered. So the amount of disorder has decreased. We can say that the entropy has decreased and is negative. Second question, explain with the help of an equation how we could make this reaction a spontaneous reaction. Well, the equation in question is the equation for the Gibbs free energy, which takes the enthalpy minus the entropy but is multiplied by the temperature, when the temperature is being measured in Kelvin. So we want this value from the enthalpy, we want it to be small. We want this value from the entropy multiplied by the temperature in Kelvin, we want it to be large. So we really want it to give us a negative value for the Gibbs free energy. So even if the reaction is non-spontaneous, we can turn it into a spontaneous reaction if we increase the temperature. Many people try to answer this question by writing a new chemical equation. Our chemical equation was already balanced. You start making up numbers, you no longer have a balanced equation. So the Gibbs free energy, which shows that increasing temperature can sometimes turn a non-spontaneous process into a spontaneous reaction. Question 2. We're looking at this reaction which shows the energy is one of the products. There's more energy coming out of the reaction than goes in. A net release of energy. We notice a net release because it looks like it's one of the products coming out of the reaction. And reactions which give out more energy are exothermic reactions. So from our starting level, just somewhere on the page, maybe about halfway to a third of the way up, this is the energy of our initial reagents, the butane and the oxygen gas. There's energy going in to satisfy the energy of activation. The energy needed to break the existing chemical bonds. So the energy of activation is also the bond breaking energy. Coming back out the other side and finishing lower than we started, the energy coming back out is the bond making energy. The energy released when new chemical bonds form. Right at the peak of the graph is our transition state. That transition state, the imagined point of chemical collisions, when chemical bonds are breaking and new chemical bonds are forming. And the difference between the energy going in for the reactants and the energy for the final products, carbon dioxide and water, that difference in energy is the entropy of the reaction. Delta H, sometimes known as our heat of the reaction. And for this reaction it's negative 453,000 calories. Because from the point of view of the chemicals, this is how much energy they have lost. A net loss of energy. Two ways to speed up the reaction. On the second page, we could add a catalyst we could increase the concentration of those initial reactants, either the butane or the oxygen. Increased concentration, more collisions and a faster rate. Or we could increase the temperature. Remember, for an irreversible reaction, the speed of the reaction normally doubles with a 10 degrees rise in Celsius. On to question 3, and we're looking at an equilibrium system. There are competing forward reactions which produces the iron thiocyanate nitrate complex, and that's red in colour. So as the forward reaction becomes dominant, the solution becomes more red, because that's the colour of the product from the forward reaction. The back reaction, which unravels this complex and turns it back into the iron nitrate and ammonium thiocyanate, as the back reaction becomes dominant, we produce more of the iron nitrate, and that's yellow in colour. So a dominant back reaction producing more of the iron nitrate would produce a stronger yellow colour in the solution. So we're asked, using Le Chatelier's principle, what happens if we remove ammonium nitrate? So there's our ammonium nitrate. It's one of the chemicals which drives the back reaction from right to left. So if we remove ammonium nitrate, we're affecting the back reaction, but we're affecting it in a negative way. We're reducing concentration, which reduces the number of collisions, and will slow the rate of the back reaction. So the back reaction is happening slower, than the forward reaction is favoured. So the position of equilibrium moves to the right. Last question. We're told that there's a rise in temperature. A rise in temperature by 11 degrees Celsius. Now we know for equilibrium systems, an increase in temperature will favour a very particular kind of reaction. It favours an endothermic reaction, which needs more energy to be put in. So the question becomes, which of the two reactions is the endothermic reaction? Well, we're also told that the colour changes from yellow to red. Red is produced by that main product from the forward reaction, the iron thiocyanate. So if the colour is becoming a stronger red and producing more of this chemical, we must be favouring the forward reaction. So the forward reaction is favoured, and ultimately it means that the forward reaction is an endothermic reaction. A rise in temperature favours an endothermic reaction. From the colour change, the forward reaction has been favoured, so the forward reaction is endothermic, and therefore the back reaction is exothermic. So as we look at our original equation, the energy term would actually go on the left hand side. Energy going into the forward reaction to drive it, the back reaction exothermic, giving off energy when the back reaction is dominant.